All right, let's look at this one. So is this due at 5 tonight?
Yeah.
So let's look at this one. Oh, so I think what I'll do is we'll do these two examples. This one, and we'll finish the example from last time, and I'll let you turn in your written homework on Monday. Because that first page, I feel like we didn't really cover it well enough. The first couple problems. So you can turn in Monday. Now that being said, I could collect it because I didn't really get any questions. No one. There was one person who requested some help yesterday. So, but I would guess that your solutions to the first problem, maybe many of you don't have it correct. So I want to give you the chance to make sure that first page with the spherical and cylindrical coordinates is right. So let's do these examples. So this one, the volume of the solid okay. The volume of the solid lies within the sphere and above the xy plane and outside the cone. Right, so always a picture, always a picture. So this cone is going to be what? Stretched vertically in the z direction times 2 from our kind of our baseline cone. So I'll draw it a little steeper here like this. And it's going to be outside of that cone. I prefer below, right? So this is a function, z is a function of x and y. So yeah, it's outside, but that really, mathematically, we're talking about below the cone, right? Below the cone. And then within the sphere, like this. So inside that sphere and outside that cone, can you see what solid that is? That's like maybe like a football stand or something like that, right? See that? It's this part over here. So outside of the cone and inside the sphere. Okay, and so we want to use spherical coordinates to do this. And so, does it say volume? So the volume means our function is 1. We're going to have rho squared sine phi d rho d phi d theta. Okay, so the question is rho goes from what to what? So when you think about the limits for rho, you think about you're the archer with the arrow, you're standing on the origin, and you're firing out from the origin, right? And so the arrow is going to pierce into the solid, and that's going to be your lower limit for rho. And then where the arrow pierces out of the solid is going to be your upper limit for rho. Okay, so we're standing at the origin, and we're going to fire from there. What's our lower limit? 0, right? Because the solid starts at 0, right? The solid starts at 0. And then what's the upper limit? So we're going to fire out here like this. And where does it leave? It leaves at rho equals 3, right? The radius of our sphere would be rho equals 3. All right, is that true for everywhere in the solid? We always have to ask that question because it may not be true. So everywhere in that solid, does it start at 0 and end at 3 for rho? And everywhere in that solid, like say on this edge here, 0 to 3, yes? Down here at this edge here, 0 to 3? Yeah, so everywhere in this solid, your lower limit's going to be 0 and your outer limit's going to be 3. Hey, what about phi? So phi is going to be all our angles. So our lower limit for phi, so we start z equals 0, or phi equals 0 is straight up. And so what's our initial angle of phi? Our initial angle of phi is going to be what? Along the cone, right? Along the cone is going to be our initial phi. It's an angle measure, right? It's an angle measure. So don't guess. Well, we'll get there in a second. And then that's going to be from phi 1 to phi, the final phi will be, you keep tipping down until you've covered all the points in the solid. So where's our phi 2? That's going to be the xy plane, right? So that one we can just say what it is. Phi 2 is pi over 2, right? It's the xy plane. So the question is, what is this phi? This angle, so this angle right here, right? This angle right here is our phi 1. It's the angle tipped down from the positive z-axis to the edge of that cone, because that's where the solid starts, right? The solid starts on the edge of the cone with regards to phi. Okay, so we can do the math here to get that, right? So this cone should associate with some angle phi because that edge of that is some constant value tipped down. So if we just use our formulas to change this into spherical coordinates, that should lead us to the angle phi, right? So what is z in spherical coordinates? Rho cosine phi? And what is square root of x squared plus y squared? That's r. And what is r in? So we have 2 rho sine. Because that squared x squared plus y squared is just r. And so we have rho sine phi. So then look what happens. Rho's go away. And we have what? Sine over cosine equals 1/2. Right? If we solve that, we could, and that's tangent, right? That's tangent equals 1/2. So what angle is our starting angle? What's our starting phi? So this cone is equivalent to tangent of phi equals 1/2. So that phi is arc tangent, right? Are you thinking that? Arc tangent of 1/2. And is it that everywhere, right? Everywhere is our starting angle, that arc tangent, and our final angle pi over 2. Yeah, yeah. And so for what angle is theta? All the way around, right? So we're going all the way around to 0 to 2 pi. Questions on this? Okay, I want to do the same problem in cylindrical coordinates. Cylindrical coordinates. So this is like your written homework. I gave you 2 setups, and you had to do them in both coordinate systems. So I'm going to take attendance. I want you to set up triple integral expression to find that volume in cylindrical coordinates. Okay, Jacob in the back there. How does this go? So tell me, what are my coordinates in cylindrical coordinates, first of all? ZR and theta, okay? And if I'm going to do the volume, what am I going to integrate? What'd you say? Just r, right? It could be 1 times r, right? The r comes from the r dr d theta, and then the 1, if we just want volume. Okay, so tell me about dz. 0 to 2r. Max, you agree with that? Yeah? Okay. Zoe, you agree with that? All right, then what about r? 0 to 3? And where's the 3 come from? Raised to the sphere. So now we're looking at dr d theta. So we're looking at what? Projection into the xy plane. So when we project this thing into the xy plane, what do we get? We get the whole disk from 0 to 3, right? And We also have what's going on here, right, at that top edge. So R goes from 0 to 3. Anna, tell me. 3 over radical 5. And where'd you get that? Okay. So you're saying that that's at a radius. When you do that intersection, you get 3 over radical 5? Okay. And then theta? 0 to 2 pi? So Anna, do you agree with that?
I got something like wildly different. Why is it not the sphere? Why is it not root 9 minus r squared?
For what?
For 0 to...
For z?
Yeah.
So for z, he's saying it's 0 to what? Square root of 9 minus r squared.
Yeah.
Well, which is it? Is it 2r or is it the sphere? Over here? It's both, right? It's both. It depends where you shoot the arrow. So dz means we're shooting the arrow from underneath up, right? First. Where does it enter in? Z equals 0. Where does it pierce out of this solid? It depends. It depends where you are, at what radius you are. Sometimes it comes out sometimes it comes out the cone, but if you're for a greater radius, it comes out the sphere. What does it mean? Just split it up, right? It's on the test. People miss it. It's on the test. And half of you, if you're like past classes, half of you will miss it. That's a warning, right? So what does this z go from? Z goes from 0 to root 9, the sphere, solved for z, right? Solved for z, and then put in r and theta coordinates. And that's from what? So this first integral was what? Where does it exit out the cone? It exits out the cone for this region here. That's showing up yellow. And now, where does it exit out the sphere? It exits out the sphere from, r goes from. So here's the part in the projection where it exits out the sphere. So that's what's when we exit out the sphere. It's going to be from what to what? 3 over radical 5 to, is it 3? Yeah. So when the radius is from 3 over radical 5 to 3, that's when z is exiting out the sphere. So our upper limit of integration is the radical 9 minus r squared, and then 0 to 2 pi. Okay, doesn't make sense. So you can do it in both cylindrical and spherical coordinates. Spherical, however, requires just one triple integral, whereas cylindrical is broken up because you have two tops, right? You have part of the top is the cone and part of the top is the sphere. Does that make sense? Okay, so going back to the example at the end of, let's do the example at the end of class last time. Let's finish that. Any questions on this? So if we did all the math, we ought to get the same volume, right? So if I evaluate that triple integral or this triple integral expression, this sum, we ought to get the same number, which is the volume of that solid. Okay, so let's look at, so we had this one from last time. We're going to do the same thing. We're going to do both in cylindrical and spherical coordinates. We had that sphere, and then we had the top of that sphere kind of enclosed in this cylinder. Like this. Okay. And so what do we were doing last time? We were doing spherical coordinates, right? Spherical coordinates. So rho. So it was above the sphere and inside the cylinder and below this, and this was z equals 5. Is that right? And this was x squared plus y squared equals 4. Is that right? And then this was x squared plus y squared plus z squared equals 4. Do I have it right? And so we're going to do rho first, right? Rho first. So rho, so we're standing at the origin. We shoot the arrow toward the solid. Where does it enter the solid? What rho value? 2, right? The radius of the sphere. And where does it exit? Where does it exit that solid? What were you saying?
Either the wall of the cylinder or the top of it.
Right. So depending on the angle phi, right? So if phi is a low value of phi, it exits out z equals 5, right? So like this. If rho is if phi is a greater angle, then it's gonna, like down here, it's gonna exit out. It's gonna exit out the cylinder. But it always enters in 2, so that means it's going to be split up, right? It always enters at 2. And we said that's going to exit, for those low values of phi, it's going to exit at z equals 5. But z is not one of our coordinates, right? So z equals 5. What is z in spherical coordinates? Rho cosine phi. And so what do I want? I want the value of phi corresponding to, the value of rho, right? I want the value of rho corresponding to z equals 5. So I'm going to solve for rho. Rho is 5 divided by cosine, which is? Remembers? Secant, right? 5 secant. Just 5 over cosine would be 5 secant. And so my rho is going to go from 2 to 5 secant, which corresponds to z equals 5. Right? That distance from that rho distance from the origin is going to change across this, right? It's the least here at phi equals 0. And it's the greatest out here at the edge. So as phi increases, that distance rho increases, right? Doesn't stay constant because this is a flat plane. So that's why it's a function of, rho is a function of phi. It's 5 secant phi. Okay? So for what angles of phi do we exit out 5 secant phi? So what's our lower value of phi? 0, because the first one is going to be coming right like this. Until what? Until what value of... So what determines this value of 5 that's the breakpoint between exiting out this z equals 5 and exiting out the cylinder? What's that breakpoint? Juyu, what's the breakpoint? Junghyun, what do you think? Where's the breakpoint between exiting out z equals 5 for rho and exiting out the cylinder? What's that? Yeah, so it's going to be when we get to here, right? When we get to that intersection of the two. So that's a particular angle right there. That's a particular angle of phi that we have to find. So how are we going to find that? Well, it's going to be for z equals 5 and r equals 2. So z equals 5 and r equals 2 should give us a particular angle of phi. So 5 equals rho cosine, right? 2 equals rho sine. So if we want to use tangent, we could do this one divided by this one, right? And the rows would go away. So we'd have sine over cosine equals what? Equals tangent equals sine over cosine equals 2/5. So what is this? This phi is arctan of 2/5. So that's that angle that's the last angle where we exit out the z equals 5. Also the first angle where we start exiting out that. So this is going to be from 0 to tan inverse of 2/5.
Why is it not pi over 2 minus tan inverse 2/5?
Because phi is the angle tipped down from.
I thought inverse tan would give the angle inside that triangle.
Tangent is what? Tangent is opposite over adjacent. Right? So this is 2 and this is 5. Tangent is opposite over adjacent. So it'd be arctan of 2/5. So that's another way to solve that, right? So you can just make that triangle, do the radius of 2, the height of 5, and just solve that triangle. So both ways are valid, right? So you can use the formulas like I did here first, or you can just make that triangle and do that. And then that's from what? 0 to 2 pi? So what about then? So I want you to finish this integral and do this problem in cylindrical coordinates. Go. So you're going to finish this integral. Figure out the limits, and then do the same integral in cylindrical coordinates.
Mark said it was, we did tan inverse 5 over 2, then it would be pi over 2 minus tan.
What's that?
If we did like pi over 2 for the tan inverse, it would be pi over 2 minus tan.
Yeah, because I guess that would be that angle there.
Okay.
But why would you do that?
Right.
This is just going around in circles and making it more complicated. Just do the direct way. Okay, let's see how we did. So, Zach, how about this row goes from what to what for this second integral?
I have it going from arctangent of 2/5, the angle we found before.
No, so row, that's phi. So what about row?
From 2 to 2 divided by sine of phi.
Okay, and how'd you get that?
I looked at the equation for the wall, which looked to be r equals 2.
R equals
and I
2.
know that r is going to be rho times sine of phi, and just solve from there.
Right, so then that cylinder is 2 equals rho sine phi, and so rho is,
And rho has to be 2 over sine of phi.
and if you want, cosecant. Either way, so 2 over sine, 2 times cosecant. Okay, and then, so for what values of phi do we exit out the cylinder, right? So for what values of phi? Starting at? Cody? Right? So it's going to start off where we left off last time, right? So where we finished off exiting z equals 5 is where we're going to start exiting the cylinder until what? Right, all the way down to horizontal, right? And that's pi over 2. And that's from Questions on spherical coordinates for this problem. So in this case, spherical coordinates requires the sum because we have two exiting surfaces for rho. We have the z equals 5 and then the cylinder. The dividing point of those two being arctan of 2/5. Okay, how about cylindrical coordinates? One or two triple integrals? Or 1 and 2. Corinne, you think 1? So you're doing dz and then dr d theta. Okay, z goes from what to what? 2. Right? So is there any other, in terms of z, is it broken up at all? Is there more than one bottom or more than one top? No, the whole bottom of it is the sphere and the whole top of it is 5, and then? R goes from 0 to just 2. And theta goes from? What did I forget? That should be a 2. So notice, it's in the cylinder. It's vertical cylinder. What's the easier one to do? Cylindrical coordinates, right? Yeah.
Underneath that sphere, shouldn't your lower bound for R change? Because you're bounded on the top by 2, but on the bottom, it's not 0 anymore because it doesn't go from the z-axis. It starts from the edge of the.
Yeah, that's what this is right here.
Oh, okay.
Yeah, what you're saying is all exactly correct. And that's right there. That's the sphere, right? So z, the lower bound of z is the sphere. Questions on this? Okay, so now we have 2 good examples. Now you can, if you need to, rework your first page of your written homework, okay? Because that's similar to those 2. Really important. Okay, so we're going to move on to the next chapter. So our exam is a week from Monday. Next exam is a week from Monday. So for recitation today, maybe Monday, Monday recitation you'll do some of this new stuff we're about to start right now. But for today's recitation, I've given Tin one of the pages of review problems for the exam, so you can just start working on exam stuff, which is all this triple integral stuff. Okay, good practice. All right, so let's do a function summary. So this course is, when you look at this whole course, it's really a survey on all different kinds of functions, right? All different kinds of functions. So for each type, we want to identify the conventional algebraic form and how it graphs and in what coordinate system. So a single variable real valued function. What's this conventional algebraic form? Symbols, just the generic symbols that describe a single variable real valued function. Anybody know? So, right. Y equals f of x, right? Y equals f of x. Single variable is referring to what? Independent or dependent? Single variable. Independent. We have a single independent variable. And then real valued refers to the dependent. So single variable real value functions take a value of a single quantity and spit out a real value. That's like y equals f of x. Okay? How does it graph? In what coordinate system? So does it graph as a surface, a solid, a line, a curve, an R2, R3? How does that graph? Or a string of points, right? So it could be a curve, right? So a string of points, like a curve or a line, in R2, right? In R2. This is most of your math career was You lived with y equals f of x, right? All right, what about a multivariable real-valued function? What's the common or conventional symbols that we would describe a multivariable real-valued function? Yeah. Z equals f of xy. Yeah, we've been did a lot of that, right? So multivariable refers to independent or dependent? Independent, right? I think you were thinking that. Multivariable is independent, right? We've got more than one independent variable, and then the function takes all the combination of those values and spits out a single real value. How do these graph? Surface, solid, string of points, R2, R3. Well, this particular one, Z, F, X, Y. Surface in R3, agree? Yeah, so these are surfaces in R3. For any point in the XY plane, you get a single point, so you're going to get a surface in R3, right? All right, how about a single variable vector valued function? Single variable vector valued function. Have we seen those before? Ryan, was that yes? So what? Yes, okay, so these were like the what? Remember this? RT. So those should be vectors. Right? So this is our vector valued function, right? You have the parameter t. And how does this graph where? So let's see here. So this particular one that I wrote, what does that graph as? Solid, string of points, surface, and R2 or R3? The way I've done it here. This is going to graph in R2 as what? A curve, right? A curve in R2, right? A curve in R2. So vectors are pointing, all the vectors with their tail at the origin. Change t, and you're going to get different points in the plane, and then it's like a string of points together will give a curve. So then we also saw, similarly, we had this. I mean, I think that's what there. Yeah, so we had this, and this was a curve in R3, right? So curve in R2 or curve in R3, single variable vector valued function. All right, what about a multivariable vector valued function? Have we seen those? We have not, and that's what we're going to do next, a multivariable vector valued function. So now you have more than one input variable, and for each combination of those parameters, it spits out a vector. So here's the ones we'll work on first. So what do we got? We got two variables, x and y. The x component of the vector is some function of x and y, and the y component of the vector could be some other function of x and y. So given a combination of a value in x and y, it gives you vectors. So let's do that. Here we go. So what exactly is this, right? So what is this thing? That you take values of x and y, and it gives you a vector. So what does that mean? That means that input is location, right? Input is location in the plane. And output is a vector. So for instance, there's one of these multivariable vector valued functions. You don't know what it is, but we're going to figure it out. So here I'm showing you that x is -1. And y is +1. And associated with that location is a vector. The x component's dependent on the location. The y component's dependent on the location. And what vector do we get? So for this particular vector function that you don't know, If x is negative 1 and y is 1, what vector do you get? You see what I'm showing you? Here's the location negative 1, 1. And that location in this function determines a vector. What vector is it? 1, 1. See that? So here's a particular, so a combination of input. The output is the vector 1, 1, and that's what that's showing. All right, so let's change it up here. So what if A is 2 and B is 0? So here A is 2, or X is 2 and Y is 0. What vector do I get for that? 0, negative 2. So as I continue to give you examples, it's your goal to figure out what is this vector function? What are those functions for the x component and the y component that determines the vector that you get at any given location? So let's do a equals 1 and b equals negative 2. So that means that x is 1, y is negative 2, and that results in the vector what? Negative 2, comma. Are you following what I'm showing you here? So I'm showing you particular combinations of x and y, or location in the plane, and this function gives you a vector for every location. That's what that function does. It gives you a vector associated with every location in the plane. Don't do that. All right, let's do zero, negative 1. Right here is 0, negative 1. X equals 0. X equals 0, y equals negative 1. What happened? Oh, sorry. There we go. So what vector is it? Negative 1, 0. Do you have a conjecture? Tell the person next to you, see if you compare. Compare with the person next to you. Vincent, did you get it? So the x component of the vector is y, okay, and the y component of the vector is negative x. Agree with that? Okay, and so if we put it all together, this is what it looks like. So every location has an associated vector, okay? If we showed all the vectors, what would you see? If we showed all the vectors for every location, what would you see? You'd see this, right? That's not helpful. So we don't show all of them. We just show them like in a grid, like we show them in a grid. And when we do that, then we get a general sense of what all of them would give us, right? So I'm not showing you every vector, but a lot of them, like kind of in a grid format, so that we can see see it. But if you showed all of them, if there's a vector for every single point there, then we'd just see all blue, right? So this is the vector field. This is called a vector field, y negative x. So the input is location, and the output is a vector. For every location, you have a particular vector, and then you can show and display the vector field by looking at lots of the vectors at once. So this particular vector field, y negative x, is like this giant whirlpool, right? It's like this giant whirlpool. If you think of like vector fields are used for describing like wind fields. So this is the wind vector field around Australia. So what we got at any given point, we have direction and magnitude of the wind speed, right? Direction and magnitude of the wind speed. So that's a vector for every location, vector field. This is flow in the English Channel. So this is a vector field of like current. Current has direction and has magnitude, right? So at any point in the English Channel, there is a vector associated with the current. And so you put them all together and you get this vector field. This one. So here's a magnetic field around just a simple magnet. You get close to the magnet, you have the higher forces. Move away from the magnet, and the strength of the force of the magnetic field due to the magnet shrinks out as you move away from it. But it's right. So repulsion, strong near that pole right there. You have strong repulsion. Near this pole, you have strong attraction. So you have the biggest vectors closest to that side, closest to the sides, and close to the magnet. You have the greatest attractionary forces, and then away you have it shrinks as you move away.